Alright, welcome to the next lesson on trigonometry. To start off, we're going to review some of the trig from earlier year levels. I would advise to pretend that this is a normal lesson and anything that I write down, copy down into your notes as well. SOH CAH TOA. Let's have a look. This is a triangle. This is a right angle triangle. We say that if we have an angle over here, then this side is going to be the opposite. This is going to be the adjacent, and this one here is the hypotenuse. I think that's spelled right. Maybe there's another E in there. SOH CAH TOA. The S is for sine, the C is for cos, the T is for tan. So, what does that mean? It means that sine from the letter S of the angle of theta equals the opposite over the hypotenuse, SO and H. Cos of the angle equals the adjacent over the hypotenuse, and tan of the angle, TOA, is the opposite over the adjacent. SOH CAH TOA. We're going to use this to answer questions relating to right angle triangles, to find the unknowns in right angle triangles. Let's take some examples. If I know that this is 30 degrees, and I want to find the opposite side, and I know the hypotenuse is 5, then I can set myself up an equation. I can say that I've got the opposite and the hypotenuse, so I've got to use sine. Sine of my angle is x on 5, and then x would equal, we times both sides by 5. 5, why am I writing cos? Let's go back. 5 times sine of the angle, which if you work out on your calculator will be 5 on 2. Let's take another example. What if we had a triangle with a right angle there, an angle of, say, this time 60 degrees. My triangles aren't really being drawn to scale, but let's pretend that that's 60 degrees. And this time we want to know what the hypotenuse is. Let's call this, I don't know, S, just for the fun of it, just for a random variable called S. And we're given that this length over here is 7. So I have here the one next to the angle, I have here the adjacent, and S is the hypotenuse, so I'm working with the adjacent and hypotenuse, and looking at SOH CAH TOA, I've got to use C cos CAH. And I can set up my equation and say that cos of 60 degrees equals the adjacent, which is 7 on S. I'm going to try and get, that's setting up the equation. The first step is to set up the equation, the next step is to solve the equation. So now I want to try and get the S by itself. So first the S is on the bottom, let me get rid of it from being on the bottom. Times both sides by S. S times cos of 60. Right, it's like S times cos of 60 equals 7. I've just times the S to both sides, and then S would equal 7 divided by cos of 60. which on your calculator, when you work it out, will be, I think it will be 14. What are we saying? That if, say, we're talking about in meters, then the length of the hypotenuse is 14 meters. Let's do one last example. 3. Say we have a triangle now. Let's make it a bit harder. So let's draw it in a different direction. And let's put the angle up there, and we'll say that angle is 45 degrees. And we'll say that I want to know what this one is. We'll call this side P. I want to find out P. And we know that this side over here is 10. So what can we see? I've got an opposite, that's the 10, and I have an adjacent, which is the P. I don't actually have hypotenuse this time. So if I have a look, I've got opposite and adjacent, TOA, T, O, and A. So I've got to use TOA. So that means I say that T for tan of my angle equals my opposite, which is 10, divided by P, which is the adjacent, times both sides by P to get P tan of 45 is 10, and then P equals 10 on tan 45. On your calculator, you get that P equals 10. So that length of that triangle is 10. So that is a quicker refresher on SOH CAH TOA and finding the unknowns of a triangle. You can use this to find all the angles or all the sides of a triangle from knowing just two. Let's make a note of that. That using SOH CAH TOA you can find all the sides and all the angles just from one side and one angle. Just a point to make, we're calling this a right-angled triangle. So using SOH CAH TOA, you can find all the sides and all the angles in a right-angled triangle just from one side and one angle. Let's do one last example. This time let's say that I've got a triangle. And however, I don't actually know what my angle is. I want to know what my angle is. There's the angle, we're like, what's the angle? But we're given that one side, the length is 3, one side, the length is 5. So we can still say that we have an opposite and a hypotenuse, which means we're using SOH. And I can say that sine of my angle equals 3 on 5. Then how do you work out what theta is? Then on your calculator you can say that theta is going to equal inverse sine of 3 on 5. Remember that the thing that goes inside a sine is always an angle. Over here, we're putting 3 on 5 not inside a sine, we're putting 3 on 5 inside the inverse sine. An inverse sine is always going to give you an angle. On a calculator, we can work out that to be on your calculator, you work that out to be 36.87 degrees. That would be the answer if the question said, give your answer to 2 decimal places. If it said give as an exact answer, then the exact answer is that. Inverse sine of 3 on 5, which is the angle 36.87 degrees approximately. So one thing to note is that using SOH-CAH you can find all the sides and all the angles in a right angle triangle just from one side and one angle, or from two sides. Right, that's what we did over here. We had the 3 and the 5 and we worked out the angle. Let's take this example. Two things to note. So I said, well, you can find all the sides and all the angles. How can you do that? If this angle over here is theta, that's our right angle. That's 3 and that's 5. How can we work out this side? So there's a few ways you could use the SOH-CAH, but I would say the easiest way to do it here is to say that we know that c squared plus 3 squared equals 5 squared, using Pythag. A squared plus b squared is c squared. So c squared equals 25 minus 9, which is 16. C is going to equal plus or minus 4, but because a side can't be negative, that negative is not applicable. So C just equals 4. So you can use Pythag to work out a third side when you have two others. And what if you were asked for this angle here? How can you work out alpha, right? Where alpha is an angle. What we can do is we know that all the angles in a triangle add up to 180. 180 is going to equal our right angle, which is 90, plus our theta, plus our alpha. So alpha would equal 180 minus 90 minus our theta. Our theta was approximately 36.87. In your calculator, you would get that alpha is 53.13 degrees to 2 decimal places. So we're all talking about degrees here, not radians. And these are just two things to note of ways of finding other unknowns in a triangle besides SOH-CAH. You can use Pythag, and you can use the fact that all the angles in a triangle add up to 180. But the main thing to get from this revision are these three examples here. Using SOH, CAH, and TOA to find the unknowns of a triangle. And this fourth example is also quite good. Finding an angle if you have two of the sides. With that, you're able to do exercise 16D. You can see there are two questions. One is practicing finding the unknowns of a triangle, and the second one is also using those same skills, but applying it to a circle, or triangles within a circle. Do that now and practice that. When you finish that, you can come back and we will continue the lesson looking at a newer topic. The homework so far then is questions 1 and 2 from 16D. Alright, so you've done that revision now, which will help you follow the proofs for the symmetry properties of sine, cos, and tan. We're going to look into some interesting theory over here, and we'll use a blue pen to start us off. So, we're going to think back to that big circle that we drew the other day. And let's set it up. Here's a line. here's our circle. We said that this is the unit circle. It has a radius of 1. Okay? Let's pretend that we have a point who has an x value of x and a y value of y. Okay? So that's the coordinate x, comma, y. It's drawn at an angle of theta, 30 degrees, 20 degrees, 45 degrees from your x-axis, from the positive x-axis. These x and y on the axes, I guess, are different to the point that we're talking about. This point has a number x, like it's 5 across, so x across, and say it goes 5 up, y up. What we can do is we can think of this circle as being, or as this angle drawn to the circle as being a triangle, right? We can think about this angle drawn from the positive x-axis to the point xy as making a triangle. The height of the triangle is y, the length across of the triangle is x. Let's use SOH CAH TOA to try and set some things up. What is sine of theta? It equals the opposite of the triangle, y over 1. And y, anything divided by 1 is just itself. Sine of theta equals y. Cos of theta is going to be the adjacent, which is x, over 1, which equals x. Tan of theta equals the opposite, which is y, over the adjacent, which is x, y on x. And interestingly, we have that y is sine and x is cos. So tan is actually also the same as sine on cos. If you look back to what we did last lesson, we actually wrote those down. Now you can see where they come from. Sine of theta equals your y, cos of theta is your x, tan of theta is sine on cos. Let's have a think now about drawing a line to another part of the circle.
Should I put Chinese dating show again?
We're going to draw it to another point on the opposite side of the circle. Now we're going to pretend that this is a symmetric circle. Okay, so we're going to draw to the point opposite. We're going to pretend that this is also theta. If that's theta, right, pretend that they're the same theta, pretend it's a symmetric circle, then this point over here, what would it be? It would be negative x, comma y. Okay, we've got negative x, so if the other side was to 5, it's now to negative 5, and the height is still at y. Oops, wrote that out. Let's go back. Go back. The height is still y. Let's think about this triangle, okay? This triangle's height is y, its length across is negative x. Now remember that sine of theta goes to the y coordinate and cos of theta goes to the x coordinate. So we can see that the y coordinate, right, should equal sine of an angle. Right? Sine goes to the y coordinate. However, we're not going to, what angle should we put inside? We're not going to put the little theta, because the little theta, if you look on the right hand side, gave us the black coordinate. If we want the green thing, we have to use the angle from the positive x-axis to that green line. What's that angle there? That orange angle is pi minus theta. Remember that this axis over here is pi degrees. You've gone around pi degrees to get to here. Sorry, not pi degrees, pi radians. We've travelled pi radians to get to this spot. That there is pi radians. Half a circle. So, sine of the angle to get to there is going to give us the y coordinate. Sine of pi minus theta gives us the y. Cos, what does cos of pi minus theta give us? If we think about the angle from the positive x-axis to that green line, and we look at the x-coordinate there, the x-coordinate in that green coordinate is negative x. And what would tan of pi minus theta be? It's the y part on the x part. So y divided by negative x. We can see here that we're starting to build up some symmetries. Sine of, if we look at the black, sine of theta equals y, right? And also sine of pi, and also sine of pi minus theta equals y. Okay? Cos of theta equals x, and cos of pi minus theta equals negative x. Tan of theta equals y on x. Tan of pi minus theta equals the negative of y on x. We can start to draw up some symmetries. Okay, we can say that sine of pi minus theta equals sine of theta. We've got that. Sine of theta is y, and sine of pi minus theta equals y. Cos of pi minus theta equals negative cos of theta. Right? Cos of theta is x, but cos of pi minus theta is the negative of that, is negative x. So cos of pi minus theta is going to be the negative of cos of theta. Tan of pi minus theta equals negative tan theta. The tan of theta is y on x, but tan of pi minus theta equals y on negative x. The negative. That's one symmetry. If you were to draw more triangles, right, and you can do this as an exercise yourselves if you like. If you were to draw more triangles and think of more coordinates, that's negative x and negative y. And this one down here is also, or pretend that it's all symmetrical, yeah, that would be x and negative y. You can actually build up many more symmetries. For example, sine of pi plus theta equals negative sine theta. Cos of pi plus theta equals negative cos theta. Tan of pi plus theta equals tan of theta. Let's get another colour. Pink. And what are the quadrants that we're in? Over here, pi minus theta, we can see is in the second quadrant. So let's label the quadrants. That's the second quadrant. That's the first quadrant. That's the fourth quadrant. So first, second, third, fourth. All of these ones in the orange were for symmetries in their second quadrant. These in the red are the symmetries for the third quadrant. And I'm about to write up the symmetries in the fourth quadrant. In the fourth quadrant, you can say sine of negative theta, so the angle but going backwards, right? If you start at the positive x and you go backwards a little bit, you end up in the fourth quadrant. Cos of negative theta, tan of negative theta. What are their symmetries? Sine of negative theta equals negative sine theta. Cos of negative theta equals cos of theta. Tan of negative theta equals negative tan theta. These symmetries are quite useful. I am going to add in that to get to the fourth quadrant, you can think about going sine of negative theta. You can also think about going sine of 2 pi minus theta. If we think about it, 2 pi is the full circle, right? You've gone a full circle, that there is 2 pi. So 2 pi minus theta would put you in the fourth quadrant. That tan of 2 pi minus theta is the same as tan of negative theta, and it's negative tan of theta. Cos of 2 pi minus theta is the same as cos of negative theta, and that equals cos of theta. Sine of 2 pi minus theta equals sine of negative theta, that equals negative sine theta. The proofs that we look through in drawing this unit circle are good to follow. You wouldn't be expected necessarily at this stage to be able to come up with them by yourselves. They're good to be able to follow. The main things you want to get out of this session here are these rules here. These symmetries become very useful when we're trying to simplify trigonometric values. Let's take some examples. So how can we actually apply these rules in our examples? If you are told that sine of theta, so some angle, we're not sure what that angle is, some angle that you're putting inside the sine, if you're told that sine of theta equals 0.3, what is sine of pi plus theta? That's the question. Sine of theta is 0.3. What is sine of pi plus theta? I can use my symmetries and I can see that in the third quadrant, so pi plus theta, somewhere in the third quadrant, if I look at the red writing, I can see that sine of pi plus theta equals negative sine of theta. But we were told what sine of theta is. Sine of theta was 0.3. So sine of pi plus theta equals negative 0.3. Okay, let's call that example 1. Let's go example 2. If tan of theta equals 20, right? What is tan of negative theta? We can use our symmetries. We know that tan of negative theta equals, looking in the blue writing, tan of negative theta equals negative tan of theta. So it's going to equal negative 20. And we'll go with one last example. If cos of theta equals 0.4, then, whoops, sorry about that. Then the question is, what is cos of pi minus theta? So pi minus theta is in our second quadrant, that's the orange writing. Cos of pi minus theta we can see equals negative cos of theta. Cos of pi minus theta equals negative cos of theta, so it's going to equal negative 0.4. We're going to look at two more examples. covering these skills that take the skills a little bit further. Here we go. If sine of 30 equals sine of x, when x is in the second quadrant, what is x? That's the question. Sine of 30 is sine of x, and x is in the second quadrant. What is x? So to answer these, we're talking about quadrants. Let's have a brief reminder about our different quadrants. We know that over here is 0 degrees, over here is pi, or pi radians, or we could say 180 degrees. Over here is 3 pi on 2 radians, or we could say 270 degrees, and over here is pi on 2 radians, or we could say 90 degrees. 0 is also 2 pi radians. When you get around here, it's also 360 degrees. The quadrants are, that's the first quadrant, that's the second quadrant, that's the third quadrant, that's the fourth quadrant. What are we told? We're told that sine of 30, so we're working in degrees because they gave the number in degrees, sine of 30 equals sine of x, and x is in the second quadrant. We know from our symmetries that sine of theta is going to equal sine of pi minus theta. Right? Sine of 30 is going to equal sine of, I could say pi, but we're working in degrees, so I'll say 180 minus 30. And we're working in the second quadrant. That's why I chose 180 minus to put us in the second quadrant. So sine of 30 is actually going to equal sine of 150. We can say x is 150. So this is interesting to see that sine of 30 is actually going to give us the same number as sine of 150. If you put both those things into your calculator, you would get the same answer. Okay, that's at 30. Let's take one more example. If cos of x equals negative cos of, say, 60 degrees, and we're told that, oh no, sorry, I don't want to use 60 degrees. I was going to give an example with radians. That's right. We'll say pi on 3 radians, and we're told that x is in between pi and 3 pi on 2. What's that telling us? It's telling us that that's pi and that's 3 pi on 2. It's telling us that x, the angle x, that's the angle x, is putting us in a third quadrant. Okay? It's putting us in a third quadrant. And if we look to the third quadrant, we can see that cos of pi plus theta is going to be negative cos of theta. Cos of pi plus theta is going to be negative cos of theta. So, cos of pi plus theta equals negative cos of theta. In this case, our cos of theta is pi on 3. So cos of, we can see from this that cos of x equals cos of pi plus pi on 3, because they both equal negative cos theta. And then it's a matter of adding them together. That pi plus pi on 3 is going to be 3 pi on 3 plus 1 pi on, whoops, getting ahead of myself there, plus 1 pi on 3, and we end up with cos of 4 pi on 3. If cos of x equals cos of 4 pi on 3, x is 4 pi on 3. X is 4 pi on 3, and that fits because 4 pi on 3 is in between pi and 3 pi on 2. Effectively, we took pi plus pi on 3, because that put us in the third quadrant, and that turned out to be 4 pi on 3. Those are the examples which help you then cover exercise 16E. And the homework there is questions 1 to 3. If you have a look at the questions here, the first question asks you to apply those symmetries, and then the other questions ask you to apply the symmetries in terms of the quadrants, like the last two examples that we were doing. You'll find that the applying of symmetries here in question 1 is something that comes up quite a bit, and that's a skill that is good to get used to, and questions 2 and 3 and 4 are more checking your understanding of the symmetries and how well you follow them. Note. There's one last thing to note that can be helpful for you to solve these problems. This picture here. All stations to Craigieburn, Croydon, Caulfield, all stations to C, right, tells you where things are positive and negative. In this first quadrant, all are positive. In the second quadrant, sine is positive. In the third quadrant, tan is positive. In the first quadrant, cos is positive. So just as an example, remembering that this is pi, sine of theta. Right, let's say where theta is small, right? It's between 0 to 90 degrees, or between 0 to pi on 2 degrees. Sine of theta, right? If we have sine of theta, that's going to equal sine of pi minus theta. Right? Sine of pi minus theta is in our second quadrant, so it's positive sine theta. If you had sine of pi plus theta, that's in your third quadrant, but only tan is positive there, so you get negative sine of theta. This is a trick to remembering the symmetries we wrote down beforehand. Cos of 2 pi minus theta, right, that's in our fourth quadrant, and cos is positive there, so it's going to equal cos of theta. But cos of pi plus theta, where's that? That's in our third quadrant. Only tan is positive there, so it's going to be negative cos of theta. If you can remember this ASTC, it'll show you, help you remember all the symmetries. I'll give you one more example. Tan of pi, the previous example, cos of pi minus theta, then we do cos of pi plus theta. Cos of pi plus theta is in the third quadrant, which is negative. Tan of pi minus theta, that's in our second quadrant, where only sine is positive, so tan has to be negative. We're going to come back to this, and we're going to mention this a few times. ASTC helps you work out where sine, cos, and tan are positive and negative, and helps you remember those symmetries.